Well, we're on to the next part, basic wave polarization, blank polarization. What's the blank?
I don't know. I guess we'll find out.
Well, let's see. We are now going to do something different. We're not going to consider H here because H is always perpendicular to E, so you can draw the perpendicular to the results that we get. Here's our electric field, as before, written in terms of cosines. The only difference is that we got a phase shift in the y component. And so that phase shift is going to affect the time here as this thing goes around. The other thing to make it easy to visualize initially is Ex is equal to Ey, and we'll freeze everything at z equals 0. So if we do all that, this is what we get. And now what we want to do is run this through different time steps for different values of omega t and see what we come up with. Recall that for the linear polarization, the vibration traced out a line, maybe up and down or off to a side. And let's see what we get this time. We're going to get a line, an ellipse, a Klein bottle, who knows. Let's start. So omega t is equal to 0. Phi is minus pi over 2. So if we look at that and you take the cosine and you shift it by minus pi over 2, you're actually starting at the beginning of the sine wave. And so our field is going to be Ex cosine plus Ex sine. At omega t equals 0, we just have the Ex component. So I want to be a little particular here, so I'm going to make sure I get the same value. That's about right there. So my Ex, my electric field value, I'm not going to annotate it, is sitting right there. Now, let's take omega t equals pi over 4.
So 45 degrees.
45 degrees. Well, cosine and sine are the same. These are the same. The vector has a x and y components the same, so it's going to be here. And so that's what the E field looks like. Not going to mess the drawing up putting E. We know that we're dealing with E. And now the next one. So when omega t is pi over 2, our electric field is fully along the y-axis. And just to give us the right scale, we're about there, there. So here's my electric field. I'll draw it like that, thicker. And let's put in the other ones. So the ones here from time 0 is right there. So that's this one along the x-axis. And now again, it's about there along the y-axis. And if we smoothly connect the points, we get a circle, and it starts at this point, and the circle traverses that way. So the building up of the circle, instead of vibrating up and down, it's vibrating along an arc. And you can imagine that if we continue, the arc will continue, and come right back, and we'll get a full circle.
That's amazing.
Well, now, your turn, Sam.
Okay. This time we're doing the phi equals positive pi over 2 scenario. So you shift the cos function in the other direction, and you start with a negative sign as opposed to that.
Okay, don't forget to use your scale. So
yep. So initially, the sign at omega t equals 0 is still a 0. So we're left with still purely an x component. So if we do that around here, why does it get worse? Well, so in the beginning, the E field is still in this direction, in purely this X direction. Looks right? So at 45 degree, just like that, but in the different Y direction, you have the E field pointing in roughly that direction, 45 degree down. That's the new E. And then at pi over 2, 90 degree, it's pointing purely down because you have sine is 1 and then is in the negative. The cos term becomes 0. So you have that.
Okay, you want to draw in the others and show
yeah,
the circle?
on this last picture, I'll follow Matt's lead and draw all 3 time steps. There's 1. So that's at initial location, 45 degree, negative 90 degree. And if we smooth it,
Oh, there's our circle. Now let's get the right-hand rule done correctly here, and we can see that the rotation is counterclockwise and it's sticking out. You can see that my thumb is indicating that the point of the vector is coming out of the board, and that's counterclockwise, C, C, W, and it's called right-handed circular polarization, RCP. Okay, your turn.
Well, following the same example, it's clockwise for me. And I use my left hand pointing out of the page.
And look at that, those fingers.
Look at the
They're pointing
rotation.
clockwise. Yeah, so that's good.
So that's a left hand, what's C again?
LCP, left hand circular polarization.
What he said.
Yeah, so now we're ready to fill in the blank.
Well, it's circular, right?
Circular.
Why don't we just say circular?
Circular. I'll do the CIR and you can do the rest. Circular. Circular, like in a circle, going around in a circle, right? That's the best we can do. We can't do horizontal circles because we can't levitate. But I want to close with a puzzle. My thumb isn't green, right? It's white.
Yep.
There's no green inside the glass. So why do I get a green dot when I push on the light board?
Why? Huh, would that happen if I put my whole hand?
Well, yeah.
Ooh, amazing. I'm
Well,
green
that's
man.
a puzzle.
That's a puzzle.
I don't get it. Why isn't it red or yellow?
Oh, green. Oh, it is green.
It is green.
It is green.
Good job.